Hi, welcome to the EEVblog, an electronics engineering video blog of interest to anyone involved in electronics design. I'm your host, Dave Jones. Hi, pretty exciting one today. We've got another EEVblog world exclusive. We've got the brand new Tektronix Mixed Domain Oscilloscope. You heard that right, Mixed Domain. Let's check it out. And here it is, the brand new Tektronix MDO4000 series oscilloscope. We'll take a good look at it up close later, so I won't wave it around now. But it's basically a new series of scopes, in fact a whole new technology, or a whole new paradigm. Be prepared for the marketing buzzwords with this one. Whole new paradigm of oscilloscopes, so Tektronix claim. Now, basically, there are three types of oscilloscopes now. Before there were only two. Your traditional time domain oscilloscope, your regular digital storage oscilloscope, DSO, whatever you want to call it. Okay, that only did time domain. Then along came the mixed signal digital storage oscilloscopes, and they combined your time domain analog and your digital logic analyzer. And now Tektronix have claimed they've created a whole new category, a whole new paradigm of mixed domain oscilloscopes. What this means is that you get three things in the one scope. You get your traditional time domain analog stuff, you get your mixed signal digital, and the third, with this scope, you get RF or spectrum, frequency spectrum capability. Hence the name Mixed Domain, MDO series scopes, because you not only combine frequency domain with time domain, but the digital domain as well. Awesome! And thanks to Tektronix, we've got one here on the review date. It's being released today, August 30th, so presumably you'll be able to buy it from today onwards, and we've got one to review and tear down on the release date. Awesome! First up, I've got to say what this oscilloscope isn't, because it's very important. There will be a lot of confusion. First up, because I know everybody will ask, it is not Tektronix's answer to Agilent's X Series oscilloscopes. It's got nothing to do with it. This oscilloscope is the MDO4000 series. It's to complement their existing DPO4000 series and MSO4000 series. So you've got your standard DPO series 4000 Tektronix scope, which is just your analog oscilloscope, your analog / digital oscilloscope. The MSO is the mixed signal one with the digital, and this one, the mixed domain, not only has the analog, it has the digital as well, and it's got the new RF capability built in. And that brings us to point number two, what it is not. It is not simply a FFT function. It is not. The spectrum analyzer capability of this is actually a true RF spectrum analyzer. It's got a true spectrum analyzer RF front end in it, as we'll see, and it is not just an FFT capability. And the third thing that it's not is just a spectrum analyzer bolted onto it. That's kind of separate. It's actually more than that, much more than that. It's completely integrated into the time domain of the oscilloscope and the triggering system, as we'll see. I won't go into it now, but you'll see how valuable it is compared to a regular, just having a separate spectrum analyzer on your bench and an MSO. Now, I think this new MDO capability is a big deal. It's a huge deal and a big step forward in the industry. And let me try and explain why here. I'm going to have a shot at it, okay? This is your regular oscilloscope, okay? Your DSO, your digital storage time domain oscilloscope, and it displays your waveforms of voltage versus time, as you're used to. And we've got frequency displays down here, like you'll see on any spectrum analyzer. You've got signal level versus frequency span down here. So that's your frequency domain. But up here on your time domain, a regular DSO will display your analog waveforms. And then along came your mixed signal oscilloscopes, and you're used to that. It displays your digital signals as well. They're exactly the same, but they're in the time domain. Okay, their amplitude or digital level, in the case of the MSO, 1 or 0 versus time. Now, the new MDO, the mixed domain, adds frequency capability to that. Now, it's, as I said before, it is different to just an FFT of this DSO, because almost all digital storage oscilloscopes on the market have an FFT capability. You can display your frequency domain. So what's different? Well, there's a huge difference, and it's quite subtle. Now, the DSO, when you do an FFT on that, on a regular oscilloscope, your Rigol or your Agilent or your Tektronix, whatever, every oscilloscope up until now with software FFT capability, what it does is it captures the entire waveform. Basically, it captures, it might even be off the screen like this, depending on the memory depth of the scope. It captures that, processes it, does a fast Fourier transform, FFT on it, and displays your frequency domain. Okay, this MDO scope displays the exact same frequency domain, but what it does, and here's the crucial difference, is that it captures a true RF frequency spectrum of it at each time point, like that, in time with the at each not quite each sample, because there's going to be like a window in there, so they're actually wider than that, but it doesn't calculate the FFT based on the entire digital domain. It captures the whole RF spectrum at each one of those points. So what that allows you to do is, when you've when you're doing a single shot acquisition, you've triggered on some condition or some fault or something like that, and you've got your data captured in memory. Not only do you have your analog, your digital, but you've also got all this frequency capture as well at each one of those time points. So when you scroll through your time domain signal, when you scroll through in the time domain, the RF spectrum window changes because you've captured each one of those spectrums. And the other crucial and key point is that it actually has a separate RF input, a proper RF spectrum analyzer input. It's got analog inputs, digital inputs, and RF inputs. So this spectrum down here has nothing to do at all with your analog signals that you're actually capturing. It truly does do 3 different domains: analog, digital, and frequency. And that's just awesome. And that is the huge difference with this with the mixed domain oscilloscope technology, and how I think it's completely game changing for those who need this sort of capability. It just cannot be beat. So who's going to use this sort of capability? Well, anyone who's designing RF systems, because especially our software controlled RF systems, Bluetooth, Zigbee, Wi-Fi, whatever these days, GSM mobile phones, anything. Okay, what it allows you to do is actually capture. It allows you to correlate, and this is the key thing: correlate what happens in your digital and your analog time domain, i.e., what your software is doing. You could be tracking what your software is doing down here in the digital space, as well as checking your power supply at the same time, and you could be checking your RF spectrum. So you may go through, okay, say that this is a digital command right here to switch on your RF transmitter. Then you will see no signal down here like this. You'll see nothing, and then bang, as soon as that comes on, bang, you will see your signal turn on, your RF power output turn on like that, and then you can watch say the spike, let's say turning on your RF actually caused, a spike or something like that on your power supply. That's not a good power supply, but let's say that it was you're monitoring the power supply, and you might see the dip like that as your RF transmitter turns on, and you might see that accidentally cause, say, a glitch in one of your digital lines, something like that. Fantastic. And that sort of correlation between your frequency domain and your time domain is something that you can't get by just doing an FFT of your DSO, because it's done after the fact. It's got to capture all this data, then it's got a software process, and it takes a whole heap of time and then displays your spectrum, and by the time you've done that, boom, you've missed it. It's useless, and because it's not a separate RF input, so you're not actually detecting. I mean, you could use the second channel of your, one channel of your DSO to measure your power supply, for example, and the other channel and to measure your RF input and actually get an FFT spectrum of that. But it's just not the same when you've got an RF input, true RF input that's capable of several gigahertz. Then, well, you've got a complete spectrum analyzer built in. It's awesome. And it's totally different to having a separate spectrum analyzer on your bench as well, because you might have that spectrum analyzer, but they're separate instruments. You might be able to cross trigger or something like that perhaps, but it's not really the same as having it built in to the same scope, when you can correlate your individual, you can correlate your RF spectrum to individual time points in the time domain. Oh, why didn't somebody think of this before? Unbelievable. And here it is. Now, the one we've got for review here is the top of the line. It's the MDO4104-6, or the 6 gigahertz RF spectrum input. Now, they add the -6. It comes in a -3, a 3 gigahertz version or a 6 gigahertz version, and it's 1 gigahertz analog bandwidth at 5 gig samples per second, and it also comes in a 500 megahertz version as well. So there's basically 4 different types, and you'll notice its appearance is virtually identical to the MSO4000 series. That's because it's based on exactly the same model. Basically, they've just added the RF capability into it. It's I am told it is exactly the same capability as the MSO4000 series. So if you ignore the RF stuff, which we're going to talk about today, this will effectively be also a review of the MSO4000 series as well. And as you can see, it's practically an identical layout, except that the external trigger down here, there's no external trigger on this one. It's probably the first oscilloscope in, I don't know, 30 years not to have an external trigger. So if you want your 4 analog channels, well, and external trigger for your analog, well, you've got to give up one of your channels. Bummer. It's not even on the back. Unbelievable. Anyway, the external trigger has been replaced with the RF input. It's got the spectrum analyzer controls here, and it's got a numeric entry keypad jammed into here. That's a real tiny keypad. The trigger thing's been moved from down here up to here in the horizontal, so it's all quite a cramped layout actually, but we'll take a look at that later. So yes, just like any good spectrum analyzer, it's got an N connector input for the RF. It is not just an FFT function, and that can't be stressed enough. It is a true spectrum analyzer, and you pay quite a few $1,000s difference, but you are getting a true spectrum analyzer module in there. And of course, it's got some basic controls you'd expect on any spectrum analyzer. It allows you to, well, switch on the RF channel just like you can switch on any of the analog or the digital channels, and then you can set the frequency span, amplitude, bandwidth, and markers and other stuff, and a numeric entry keypad up here, which is tiny, that allows you to actually enter direct frequencies and other numerical values as well. So pretty much it does have all the basic controls of a spectrum analyzer. Now, although they shouldn't be directly compared, just for a size comparison, I've put it next to the Agilent X Series oscilloscope here, and as you can see, it's a fair bit taller and a fair bit wider as well, and it's a fair bit heavier. It weighs around 5 kilos, which is a little bit more than the Agilent. And one of the things you first notice is the gorgeous, huge XGA display. It's 10.4 inches. There it is. Whoa, compared to 8.5 on the Agilent 3000 series. Not that, as I said, you should compare them. And the depth is, if you take a look here, the depth is pretty much identical. And on the side here, there's a 4mm earth-in banana socket as well, so you can plug your ESD wrist strap into there, or anything else you wanted. And of course, we've got our another chassis earth here, and we've got our probe test output hooks here. I rather like those. And as is common with the other Tektronix series scopes, you get two little plug-in modules behind this door here. They're just little PROM modules which actually enable various software functions which you can pay through the nose for. I don't particularly like this way of doing it. I like the Agilent's software keys better, because you know, if this is in the lab and somebody can just come along and steal one of your little modules, bingo, capability's gone. I don't like it. And you guessed it, made in China. And look, they're totally proud of all the patents on this thing. Go figure. And on the back here, there's actually 4 tapped threaded screws in there. So obviously something's designed to plug into there. That's one of those security lock cable things. You can plug an anchor cable so people don't steal it in labs and stuff like that. But I'm not sure what those things for. And there's this recessed cutout here, so obviously there's some sort of module which is designed to go on the back there. I'm not sure what. And as for the connectors on the back, we've got an auxiliary output here. We've got a 10 megahertz reference in, so if you've got a 10 megahertz, a very accurate 10 megahertz reference in your lab, as a lot of good labs do, then you can plug it in there. It's got a VGA video output, which we'll try. It's got a 1 gigabit LAN Ethernet interface. This is all standard, by the way. You don't have to pay extra for this. It's got USB device and 2 extra USB hosts along with the IC mains connector. Beauty. And let's talk about the interface, shall we? Well, the first thing that strikes me is, isn't it damn well cramped and complicated? I mean, all this stuff has been pushed, all this RS stuff has been pushed in to the exact same size case as the regular MSO4000 series. And one of the first things that strikes me is this huge control up here. It reminds me, it brings back, memories of the old-fashioned massive horizontal time bases on the analog scopes, and it's beautiful. I love it. That's actually like a force feedback kind of, it's not actually a an optical, well, it is an optical encoder, but it's not actually a knob. This one here is a knob, and you immediately think, just by the size of it and the dual layered nature of it, that is the horizontal time base, but it's not. Here's your little horizontal time base. Look at this pissy little knob here. Oh, it's horrible. The first thing I did when I turned on, I always reach for that. It's the horizontal time base, and I goof it up. It's not. It's the big wave inspector, ooh, which is actually a great capability, but look at how much space this wave inspector is everything. I can just see them sitting in a meeting going, we really need to, it's all about inspecting the waveform, and we need to make that big and prominent and everything. Let's do that, shall we? And everyone agrees and nods and grunts, and so there it is. It takes up all your front panel. There's 2 big multi-purpose knobs here. No, having one is not good enough. They've got to confuse you with 2, as we'll get into later. But that's it. That's the horizontal. That's the entire horizontal thing. You've got your acquire menu, which brings up your soft buttons as well, but that's it. One, boring. I don't like it. Trigger, once again, very simple. Your vertical is pretty standard. I like it. There's no problems with it at all. You've got your 4 channels, and they are color-coded. I don't particularly like that the buttons are the same, that the buttons are actually the color as what they actually light up to. So that's actually a yellow button. It lights up yellow. I much prefer just to have it clear and light up yellow. It doesn't actually have to be a blue button and a pink button and a green button. Ugh. And they're probably not as bright as they could be either. That pink one there is probably, that's hard for me in the reasonably bright labs here, lights I've got in the lab here. It's really, it's a bit difficult to actually see that that's turned on. So I don't particularly like that at all. Same with the run stoppers. They're all a bit dim. They're not super bright, or almost too bright like the Agilent ones, but you know, it's just a minor thing. Another thing I'm going to have a rant on. We don't have a button here. Look, it's just, it's missing. But I can kind of understand because they have other stuff like the clock and other features there as well, I guess. Whatever. But what's going on with these vertical soft buttons? They're not centered. They're offset. I hate lack of symmetry like that. I don't like it. Why? Why is that? Why aren't they actually in the center of the display? I don't get it. Now, while the optical encoders, they've got a nice indent on them, these soft ones don't. They're just an optical encoder, but the horizontal and the verticals actually have indents, and they feel pretty good. But they're the only knob on this entire thing which is actually pushable is the level, which sets the trigger level to 50%, and it takes a while too. Look at the hourglass come up there, clunk, clunk. The scope's pretty slow for a lot of stuff, as we'll go into later. But yeah, why can't why can't these be pushable and you can set the fine adjustment? I don't get it. I mean, check out how easy that function is. That very simple basic function of your fine vertical scale is on the Agilent scope here. Look, you push it and it goes, you're in fine mode, and you can adjust it. There it is, 46 millivolts. There we go. Nice, easy to adjust. You push it again and you're back. Bingo. But if you want to do that same thing on the Tektronix scope, it's a chore. Let's try it. Go into the vertical menu here. We have to go into more, and then we've got to choose thankfully it's the first option. If it wasn't, then look at this annoying function, right? This little box here pops up, right? Let's take a look at it. This little box here pops up, and you think that, okay, is it related to that button? No, of course it's not. It's an adjustable function, but it's next to this control, which is the B control, but it's got a little A there. You've actually got to use the A control up here to then adjust the fine scale, and there's a lot of lag on that too. I don't like it. It really doesn't update very well at all. But why doesn't that appear up here next to that button? The user interface on this thing is just terrible. And here's another annoying thing. When you're actually done, you think that you would push this select button, right? There it is. Oh yeah, it's select. That's what that's what I want. Get rid of it. No, the menus don't automatically disappear on you. It's really annoying. You've actually got to go menu off to get rid of it. And yes, ladies and gentlemen, we have a soft power button. Here it is. I actually kind of like the design of this. It's really nice. It's recessed and angled in there, so it's really hard to accidentally hit. But unless if you had something on your bench, like you had a screwdriver or something like that, and you went, oh, bang, oops, oh, maybe, I don't know, but that's a bit too much. But look, it stays on. Why? This is the only bit of gear in my lab which has an LED that is for standby power. Give me a break. Let's switch the lab lights off here, and boom, it's blaring. It's absolutely blaring away. This is terrible. God, this ain't some consumer toy. And how much does it draw on standby? Good question. 4.8 watts. God, fly to Jupiter on 4.8 watts. You got to be kidding me. And that's a power factor of minus 0.2, almost 24 VA. Crazy. And how long does the stupid thing take to boot up? Well, you don't really want to know, but here you go. Oh, for goodness sake. Boot! Come on! Oh, this is painful. That only took a minute and a half. What am I complaining about? Yeah, right, you can run the bloody mile in a minute and a half. Give me a break. And when it's switched on, it uses 143 watts, and that is 151 VA at 0.95 power factor. There you go. And if you switch on the RF, it doesn't really increase that at all. And how loud is it compared to the Agilent scope? So I've got the Tektronix here, the Agilent here. Let's give it a go. I think the Agilent is much quieter. I won't bother with an actual SPL measurement, but here's the Agilent. And let's give the Tek a go. No, you can hear the bearing noise in the fan. It is definitely louder. And it's rather disturbing. In a quiet lab, it is actually quite loud. I don't particularly like it. One of the things I really like on it is the tilt-in bail slash carry handle. It's a full width one, and it locks into 3 positions like this. You don't have to do any dicking around on the side like that. It just locks into a position like that. So you could actually have your scope, if you used like a right angle mains plug down there, you could actually have it sort of slightly elevated like that, or you could actually tilt it all the way back down like that. It locks into position down there like that, and that will stop the scope falling backwards if you accidentally knock it. Now, the manual does actually recommend, if you're going to use it extended with the feet like this, you must have the tilt-in bail down like that, and it lines up perfectly between the tilt-in bail, the rubber foot, and the front tilt stand like that. So that's a lovely bit of design, I think. And if you did operate it up on the feet like that with the tilt-in bail up, then, well, yeah, I could see how this thing could certainly tip over relatively easy. You wouldn't have to knock that much for your whole scope to fall over on your bench. Oops. Now, there is one thing to note with this, one problem. I mean, compared to the small little carry handle on the Agilent there, which just sort of folds away nicely and gets out of the way, if you fold this back, of course, like this, it does actually take up room on the actually behind the scope on the bench, and that could be rather annoying, but it doesn't actually touch the bench down here, so you can still have, you know, items scattered all over your bench like that, and it would go under them. But yeah, I guess it's you know, pros and cons both ways. It's a nice tilt-in bail, but it could get in the way. As you no doubt gathered, I'm not particularly thrilled with the design of this thing and the looks. I mean, check out this sort of cream color they've used over here on the RF panel. I don't know, it's just it just seems a bit, not cheap, but just, you know, not as well refined as, say, the new Agilent 3000 series. It's just pretty bland looking, I think. I don't know, but it's big, and the thing is, it does take up a lot of space on your bench. I mean, you know, check out, you know, there's my bench, and that scope takes up an awful lot of that bench, let me tell you. And if you compare, you know, if you're trying, I wouldn't actually be able to fit it up there in my rack. Actually, it's actually too high for my rack. So what do you do? I don't know. I guess that's the penalty you pay for this huge 10.4-inch display, really. I mean, I guess they've done their best to try and make it small, in, you know, as small as they can with such a massive display, because all the controls are really quite cramped in there. And just like other Tektronix scopes, there are 2 module ports here for the various software options. This is the limit module. They gave me a whole bunch of them, and they just slide in here like this. They're just little proms with, you know, a serial code in them, and they just enable the firmware, which is, the firmware is already built in. These things just enable it, basically. And I don't like this concept at all. I much prefer the software license key used on the Agilent scopes. Why? Because people can steal these things. These are bloody expensive. These can cost thousands of dollars each, and people can just steal them, and you can only put 2 in there at once, so you've got to store the other 2 somewhere else. So you could be racing around, oh, where's my USB triggering module? Oh, I can't find it. It's hopeless. I don't like it. And if you thought the Agilent software modules were expensive at like $500, well, come to Tektronix, folks. Look at this. $1,380 for the embedded triggering module, $1,530 for the USB triggering module, and bargain down here for the limit testing, only $845. But this is only some of them. There are like 12 different options apparently, and the auto version for auto car triggering Can and Lin. There's one with a flex ray module. It's $4,790. And if you want to do something real basic like trigger on an RS-232 signal or an RS-485 signal, pretty basic stuff, you want to analyze it, $1,380. You got to be kidding me. Come on. Half the fun of getting a new scope like this is opening the box. Let's check out what we get inside. All right, what do we got? We've got first up, we've got a front cover. Beauty, it just slips on the front like that. Sweet. Love it. All right, what else do we get? We get a real manual, a real paper dead tree manual, and it's all in English, the whole thing. And it does actually really look good. Beauty. You get a carry bag. I like it. Looks pretty good. Or at least I got one anyway. If I had to ask for one, if you're paying this sort of money, make sure you get your carry bag for it. We've got an accessory probe pouch. I have no idea how this works. It's got like plastic straps on the back. Where does it strap on? How does it strap on? I don't know. Beats me. Whatever. All right. We've got some logic probe accessory sets with all the little various probe hooks and ground points and stuff like that. Beauty. Okay, we've got a N to BNC connector because it's got an N connector on there for the RF, and most people will a good majority of people will want to use BNC, so beautiful. Okay, we've got some probe things. We've got the CD with software, the product documentation as well. Whoop-de-doo. We've got a power cord. It's one of these funny Yankee ones. Doesn't even work here. And we've got our logic probes, which we'll take a look at. They look really good. That's 16 channels worth. Please read this. Please update your firmware, because the firmware in the box probably has got bugs in it. So, what else we got? We get 4 probes, because this is only available in a 4-channel version. So these are the TPP1000 probes. These are the 1 gig ones. So beauty, nice probes. And you get the application module installation. What? You just plug it in, don't you? I don't know. What do you need that for? And how to use the logic probes. And we've got, looks like, a CAL certificate. Beauty. And, well, is that it? Yeah, that's a bit. Oh, I forgot. Make sure, if you're paying 20 to 30 grand for this sucker, make sure you ask for one of these demo boards. I don't know if it comes with it. I specifically asked for it because I needed to test this thing. But for this sort of money, you'd want the bloody demo board. Let me tell you, it's got a whole bunch of useful signals that you can learn how to use the scope and what features it's got. Beauty. Highly recommend you get one. If they don't include it, they damn well should. Don't get too excited about the CAL certificate. It does actually have the sticker up there. You can peel it off and put it on your scope, but it doesn't have any test results or anything like that. So some companies may or might not find that valid. These are the probes you get with it, the TPP1000. It's a 1 gigahertz passive times 10 passive probe, a pretty low 3.9 picofarads input, and I don't like this case at all. It's plastic, it's light, it feels really cheap and nasty, but I do like how it interfaces with the scope. Check this out. It's shaped to fit exactly for the input of the scope, and it's got the probe sense thing there, and you just push it in like that. There's no screwing to be done, and you can't pull that out. So I really like that, even though it's all plasticky, but to get it back out, you just have to push your thumb down on that and pull it out. So I think that's really quite a nice concept. I like it. And you get 1 spare probe tip with each one, and that actually screws into the top here. Of course, you get the grabber, and if you take that off, you can unscrew that, and there you go. That screws in, so you can, if you bust your probe hook, which happens, your probe tip, which happens, you know, can actually happen, you can actually replace it. So I like that. You also get, with each probe, you get 4 ground low inductance ground attachments, and that's great because you're always losing those damn things. So I like the probe itself. It's small, it feels good, but yeah, I don't like the plasticky case. Whatever. Now, not only do you get the standard easy hook like that for the probe, but you also get a little mini grabber. Fantastic. As for the logic analyzer probes, I don't mind them at all. They seem very high quality. They're all individually numbered and color-coded for the 16 channels in 2 separate pods, and I like the concept of the clip-in like actual module over here. I'm a bit disappointed that it doesn't use a standard 0.1 inch header on there, but whatever. You know, you've got to buy the custom probes anyway, really, and it locks in place like that, and to pull it out, you go like that. I like it. It's rather nice, but it does have like a wax it's almost like a conformal or wax coating or something over the leads. I'm not sure what that. I'm not sure if that's a coating or that's part of the they're using a special type of PVC or some sort of material there, but it just feels a bit weird. One nice feature is that you can have a central ground point from the input module like this, and they actually supply you with the spade to 0.1 inch kind of, you know, pin header thing, so that you can do a one central ground over there and not have to use one of your flying leads. Now here's a bit of a fail. We've got the demo board here, which I really like. It's got a ton of test signals on it and RF, and does the whole works. It's beautiful, and it comes with this nice split USB cable, which has power only, so you can power the board. There's no DC jack on it. You've got to power it from the USB. But if we plug it into our USB host over here, fail! It doesn't boot up. You can probably see that little LED flashing over there and the one flashing up there. It's like it's resetting, okay? And it doesn't matter if I use the ones on the back or the one USB hosts on the front or on the back. It doesn't work at all. Yet if I plug it into the USB on my Agilent up here, no problems at all. It works exactly as it does when I plug it into a notebook or into a 5-volt USB wall wart adapter. There we go. It's not resetting, and it's switched on, and it can go through the various modes. Huh? What's up with the USB hosts on here? They obviously can't provide enough current. I don't like it. Let's try a demo, shall we? We'll try the multiple peaks one first. So you press this mode button here, and it switches down to multiple peaks there. And if we go into our scope over here, if we hit the utility menu, and then it pops up and we can actually choose demo down here. So we've got to go over once again this silly A thing. It tells you to use the multifunction A button. So if we go down and select demo down there, and once again you don't actually select a menu item, it just automatically pops up. But there you go, here's all the demos built in. Unfortunately, unlike the Agilent, there's no built-in test signals. You've got to use the demo board to do it. But anyway, multiple peaks, and that gives you all the info you need to how to plug it in and how to do it. Really quite nice. And then you just go recall, and it sets up the scope, and bingo. And once again, it just stays on the screen. It's okay, I guess, because you might want to read the instructions still, but I just find that rather annoying. Anyway, bingo, there we have it. The multiple peaks demo, and we can play around with that. I like it. Now it's put us into full screen RF spectrum analyzer mode, and that's where these buttons down here come into play. You hit the RF button over here, and it comes up with the various menu options for the RF. And this is where we can start playing around with the various options here. Now the first thing you'll notice are these auto markers up here. It's automatically detected the highest reference point. It's centered that in the center. In this case it's 2.4 gigahertz at minus 18 dBm, and then it's automatically detected the other peaks, and it's put markers in there. That's a fantastic capability. Most usual spectrum analyzers, you've got to dick around with the markers, you've got to move them across and spend ages just trying to mark and figure out what the exact peaks are, but this detects it automatically. It's brilliant. I like it. And you can set that to an absolute value or to a relative value as well. And if we press spectrum traces down here, we've got the menu that we can turn on, say, averaging. Check it out, and the white waveform there is the average, and we can turn off the normal one if we want. And if we just have the average there, if you want to increase the averages, once again you've got to use the A button up here, not the B button, don't get confused. And you can have, there we go, we've got 512 averages, and you can see that these peaks in here really come out. Like if you don't have that averaging switched on, you can get that peak in there, but this peak here sort of just vanishes. But when you switch on averaging, bingo, it really comes out of the noise. There it is. I like it. And you can do the exact same thing with maximum values as well. So it finds the maximum one, so you can turn off the average, and that's just the maximum peaks. And you can do the same for the minimum as well. Once again, the minimum's gone off the screen there, but there you go, and you can switch them all on at once if you want, so you can have the average and the whole lot. I like it. It's a really nice spectrum analyzer. Another one of the annoying user interface quirks that they just haven't put much thought into. Look, if I call up Spectrum Traces here, up pops the Spectrum Traces menu, and okay, they're aligned with the buttons, great. You might think I'd be able to turn normal off, but I can't. Because like this one is highlighted down here, I've got to go up there, press it once, it highlights it, and then I'm allowed to toggle it. What's the deal with that? It knows that's the menu item. Why can't... When I press that button, it should just do it. It should just toggle. It shouldn't have to highlight first. That's ridiculous. And down here, it's got various detection methods for finding the peaks. And you can, at this time, it's fully auto mode, which, you know, a lot of the time you'll want to use that. But you can put it into manual mode. And you can, for the normal, you can actually detect the positive peaks, the negative peaks, the averages, the samples. It's really nice. It's got quite a lot of flexibility. And if you hit the More button down here, then you can do RF signal path compensation. That compensates for temperature drift and stuff like that. It takes 3 minutes to do. I've tried it. It does do it. It tells you the last time you did it was 6 hours ago. And I really like that. You can actually get better accuracy and compensate for various environments when you move the instrument to another lab at another temperature, for example, or outside into the field. And if you go down here to probe setup, you can choose voltage or current probes and the attenuation settings. And it's a reasonably decent spectrum analyzer in terms of dynamic range too. It's quoted as having a dynamic range of -60 dBc, which is pretty good. So if you see the peak here at -18 dBm, it allows us to get down reasonably low. It's very usable actually. And if we hit the markers button here, then it gives us a bunch of menu options here. And as I mentioned before, you can, the markers up the top, you can go into a delta mode, and there it is. It's a delta frequency there of, look at that. The center frequency is 2.4 gig, and then it's a 1.92 megahertz to the next peak at -10 dBc. Beautiful. And you can set up the automated peak markers. You can turn them off and on, and the thresholds, the various thresholds that it uses to actually detect those particular markers. It's very flexible and very usable. I love it. And you can see that if we adjust the excursion threshold here, it will eventually, these other markers will switch on. So it's only detected that one, and then it will detect the other two, and then it will detect the others. Up to, it looks like you've only got a maximum of 5 markers though. And of course it's got your traditional manual markers, so there you go, you can adjust those, pull them across, and it automatically detects it shows you the peak value there, and you can use the other control to move it across. If you want to get, say, that one down there, you could, no problems at all. And as you can expect, if you hit the bandwidth button on the right over there, you've got various options. You can choose various windowing capabilities. Kaiser is the default, but you can do the rectangular, Hamming, all the usual suspects. And you can change the span as well, and there you go. It's only 20 to 1, 100 to 1, and it gets better and better as you go up. And if you choose the amplitude button over on the right hand side, then you get the various amplitude controls, and that's pretty much it. And there we go, I just hit auto level, and it's just done everything for me and set it up. So that's pretty much the full, there's probably quite a few more hidden features in there, but they're the main functions, at least, of your frequency control down there. And it pretty much works as you'd expect a regular spectrum analyzer. It's quite nice with these automated markers. So I think they've really got a win here with the spectrum analyzer. But there's one other huge step forward with the spectrum analyzer capability in this thing, and that is what's called the capture bandwidth. And that's how much RF spectrum it can capture in one go. In the case of this new MDO scope, it has a capture bandwidth of 1 gigahertz. It is absolutely massive. Most other spectrum analyzers on the market have a capture bandwidth of 10, 20, or maybe even 100 megahertz, order of magnitude lower kind of stuff. And if this MDO had a capture bandwidth that small, then it would have to sweep across. What they do is they actually sweep across the whole spectrum, actually gathering the data, and then you wouldn't be able to get these quick entire spectrum captures and updates to actually enable this MDO technology like we talked about here. So it can just go snapshot, 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 snapshot. It doesn't have to sweep across the entire range. That takes time, which means that you wouldn't be able to capture the RF spectrums this quickly. So just from that aspect alone, this is worth getting as a spectrum analyzer. It's brilliant, and especially with the large spectrum jumps and the large differences in frequency spectrums in today's modern RF technology, then capture bandwidth of a gigahertz is pretty much essential these days, I think. And here's a beautiful feature. Let's try the spectrogram. Oh. We can go into the demo. If we go into the utility down here, hello, there we go. Let's go into the demo and spectrogram demo, and let's set up that, because it's probably, there we go, it's set it up a bit better, and beautiful. And you can see the spectrogram build up here. It's absolutely beautiful. Now, what this spectrogram represents is it basically takes this spectrum, okay, and it flips it like that. It flips it 90 degrees like that. So what you're seeing now, if you look at the if you see these peaks in here, it correlates. You see how that peak there is drawing that intensity there. It's got that sinusoidal sweep on it. So what is this useful for here, you ask? Well, as you can see, it's useful for very slowly varying RF signals. This is varying in real time here, so it's very slow, but it's good for seeing drift and things like that. So what does this spectrogram actually represent? Well, it in this case, the x-axis represents frequency, because we're using a spectrum analyzer. We're in the frequency domain. So as you can see, it's sweeping back and forth, and this is the actual frequency. So that's the x-axis. The y-axis, of course, represents time. You can see it slowly moving each, a few times per second. It's moving up. So that is actually time. This is the latest time down the bottom, and that's the previous time up there. And the color actually represents the amplitude. So the higher the amplitude, the darker the color you're actually going to get. Well, it turns out white is a higher amplitude than the blue background, color there. So that's a spectrogram, really useful for looking at RF drift and slowly varying RF signals. Now I'm going to show you what this 1 gigahertz super wide capture bandwidth can actually do, where it's actually useful. Now, what I'm doing here is I'm capturing an RF signal. Okay, so I've captured it. It's in stop mode, so I could disconnect the inputs, and we've got a RF spectrum down here which shows a carrier frequency at 900 megahertz. So our RF transmitter is putting out 900 megahertz at the moment. Up the top, we've got our time domain display, and these are both captured at the same time. Okay, and this pulse here, this trigger pulse, actually switches the frequency of the carrier from 9 megahertz to 2.5 gigahertz. And as you can see, there's no 2.5 gigahertz signal there at the moment, because this yellow bar here represents the time period within which that frequency spectrum was captured, and it was all captured at once. Now, what we can do here is we can pan across. Okay, we can use our pan control here to move our window across, and as you can see, as we move it, it's captured a frequency spectrum each time. And you see our carrier frequency at 900 megahertz. Whoop, it's starting to drop. There it goes, because we're at the period where our trigger pulse has actually switched off that frequency. And if we keep moving it over at the moment, oh, here we go. We're starting to see another carrier switch on. There it is. Bingo. 2.56 gigahertz. There's our other carrier after the time period. So as you can see, it's captured all of that within that tiny time period, like 1 microsecond per division there. It's absolutely tiny. And that's what you get with a super wide capture bandwidth. It's awesome. I love it. And if that wasn't good enough, let's take a look at an even more powerful example that shows just how brilliant this thing is. What I've done here, okay, what I've got is I've got a VCO, a voltage controlled oscillator, okay, and it's designed to operate at 2.4 gig. Okay, now it's what we've got here is we've got digital signals. We've got an SPI bus here. Okay, there's a little SPI packet. We've got the VCO enable pin here. We've got the phase lock loop voltage, the PLL voltage, and what we're doing basically is we're turning on the VCO here. Okay, a voltage controlled oscillator. We're switching it on, and we can watch our PLL voltage ramp up just as we could on a regular DSO. We can on a regular mixed signal oscilloscope. We can even look at the SPI packet data. We could zoom in on that and actually see the data packet if we wanted. But what we get here is because we've also got the frequency domain as well captured at exactly the same time. We can actually look at the frequency as the frequency of the VCO as the PLL voltage changes and see where our VCO, how long it takes for it to become stable. This is so brilliant and so powerful. Let's have a look at it. Okay, once again, this little orange bar here represents our frequency spectrum at that point. As you can see, it's before the VCO, we turned on our VCO here, so there's no frequency output at all. Okay, there's no carrier signal at all. But as soon as we switch it on, bang, here we go. We switched it on. There we go. We're switched on. There's our command as well. So we've turned on the VCO and we've sent our command. We're sending our command to our voltage controlled oscillator, and you can see the carriers at 2.2 gig. And as we scroll across here, we can see the frequency slowly changing. 2.8 gigahertz. There you go. 2.3, 2.3, 2.309, 2.317, 2.348 gigahertz. And as you can see, because the phase lock loop isn't stable yet, it's still moving. But as our spectrum moves across here in time, in the time domain, so this is where we're comparing this is where we're using our cross domains. We're using our frequency domain and our time domain with our mixed signal digital as well, thrown in for good measure. And as you can see, it's starting, bingo, right about now it's 2.4 gigahertz, spot on. And there you go, it's stable, bang. So it takes roughly that amount of time for it to become stable, and you can see that on the PLL voltage. Brilliant, how incredibly powerful. Oh, you've got to get one of these babies. And just remember, you wouldn't be able to do this on a regular DSO with FFT capability, even if it had a high enough sample rate to actually get a 2.4 gigahertz carrier and then do an FFT of it. You would need a massive amount of time to actually sample that. But because we've got a frequency spectrum analyzer built in, it's easy. It just captures it. Brilliant. And this is where our wave inspector control here is very nice. I've got to admit, it is one of the better features of the Tektronix, these high-end Tektronix scopes. It really is nice. And once again, the outer ring is the pan, so it allows us to pan the window across. Now I've zoomed in here so we can actually see the SPI packets here, and as you can see, it's got another little display up here to show you where in the memory, that's the entire memory depth of the scope from side to side there. And that little window, if we use our zoom control here, which is the outer one, we can actually make that smaller, and we're zooming in, or we can make it bigger like that, and you can see, so that window there correlates to what you're seeing on the display, and that yellow bar there correlates to our frequency spectrum there. So we can, depending on how much sample memory you've chosen, you can zoom in as far as you like, and we can actually see the data bytes in the SPI, on the SPI bus in this case. But you've got to have the SPI analysis module to actually do that. And of course, you've got a play and pause button here, so you can actually just press that play button and it just auto scrolls across, just like you can get on the Agilent scopes as well. And you can change the change the direction using the pan button like that, and you can zoom in and zoom out at the same time, and you can make it go faster by just moving your outer pan controls. Zoom, great fun. And you've also got markers as well, which can be handy for actually actually marking events and stuff like that, so actually time correlated events. So you just press mark there, you can see it's put a triangle at that particular point because that's where we had the rising edge. And say you wanted another one where the VCO, you know, started to the PLL started to mark up there, you could set another one and then maybe another one out here if you had some other event, and then you could just jump between the events. So that's, you know, that's pretty handy, but that's pretty standard on scopes these days, but it works well. And we get on to more of the oscilloscope features now, and it's got search capability as well. You can actually search for events in the stored domain. If you turn the search on and you choose the different types here, edge, you can search for runt pulses and rise and fall time variations and things like that. So that's fairly powerful. If you hit the test button up here, and you've got various application modules installed in this mask limit testing and power analysis. If we choose power, if we switch on the power thing, we can measure stuff like the ripple, power modulation, the safe operating area. Absolutely brilliant. And what else have we got? Power quality. Switching loss. I haven't actually got these hooked up to a switching power supply or something like that to actually measure stuff, but that looks like incredibly powerful functionality if you pay for it. Let's try the dreaded auto set button, shall we, and see what we can see how long it takes. And hey, it's jumping around all over the place there. It looks like it's gone into partial safe operating area graphing. Bingo, it's up. We've got ourselves a waveform. Okay, Tektronix, it's time to explain this one. I can understand why you've gone for 5 vertical divisions each side of the center graticule. Here, you've gone one more than the traditional 4. Fine, but then we end up with a non-square graticule like that. I just find that rather disconcerting. I don't particularly like it. And here's another thing which I'm going to do. Let's take a look down here at the horizontal. Okay, here it is. Horizontal, 100 nanoseconds per division, no problem. Let's take it back 200 nanoseconds. It's gone the 1-2 step, no problems. You expect it to go in the traditional 1-2-5 step. 1-2-4, 400 nanoseconds. What? Every scope ever invented has steps of 1-2-5, 1-2-5, 1-2-5. Why 1-2-4? I don't get it. And we can change the graticule type here. It's in the utility menu down the bottom here, and we can change it to a standard grid, solid. I kind of like that one, and you can use the intensity and the intensity up here, and you've got the A and the B control. A controls your waveform intensity, so we can turn that waveform down. There we go. And we can turn the graticule intensity down. I actually prefer just the solid, the old traditional solid line one like that. And here's a neat feature down here. We've got the trigger frequency readout. So if we switch that on, bang, we got our trigger frequency down here, and it shows that we're precisely 3.57141 megahertz, and that must be done using a hardware frequency counter. And we can do a snapshot here. We can add some measurements and do a okay, or a snapshot of all the things, just as you can get on most scopes. Fairly basic. But I'm not really keen on the process of having to go into add measurement here, select your source, use the A button here, and then use your B button, your B knob here to select these sort of things. But it's just personal preference. I guess you get used to it. But once you are in this menu here, it is easy to just go across. Once again, I prefer that button to be pushable, so that you can just move along and then push, something like that. That's much better. But anyway, I've added a couple of measurements down here, and we've got our peak to peak, our rise time, our fall time, and our frequency. So that's pretty good, and you can get and it automatically displays the mean, the min max, and the standard deviation, and you can get histograms as well. And you can get a vertical histogram here of inside that rectangular box there. Brilliant stuff. I love it. And of course, one of the big impressive features of these series scopes are the 4000 series, not only the DSO, MSO and the MDO, they've all got 20 meg points memory, and you can change that by going into the acquisition menu and hitting the record length. And once again, you can't just press that and cycle through like you can on the Agilent ones. I much prefer that. You've got to go over to the button, of course, the knob, sorry, and you can select anywhere from 1000 points per second, and it's much faster at the lower ones. I believe 10k sample memory is the default, 100k, 1 meg, and then you go up to, you know, all the way up to 20 meg. Fantastic. As I said right at the start, this oscilloscope and all of the Tektronix ones are no match for the new Agilent X Series oscilloscopes in terms of speed and just waveform updates per second. The Agilents have got 1 million waveform updates per second, and you've seen that. So I know you want to see it on this one, so I'm going to show you. What I'm generating is a signal that has a glitch pulse once every 1 million cycles. Now, this the 4000 series Tektronix ones have a claimed 50,000 waveform updates per second, and actually maximum, so that's 20 times less than the Agilent's 1 million. So we'd expect to capture this 1 millionth pulse roughly every 20, not once per second as you do on the Agilent, but every 20 seconds or so. So if we clear the persistence like this, basically on average it'll be 20 seconds before it captures that. It may capture it before, may capture after, but if you do a whole bunch of them, on average, it hasn't captured it. Oh, bingo, there we go. Was that 20 seconds? Near enough. So I've set this to infinite persistence here so that it will actually, oh, it just got another one there, exactly the same. And as you can see, it is, but here's the key. I'm in the record length of 1K, and it doesn't tell, the specs don't tell you, at least not that I could find, what the waveform updates per second were at what record length. And I think as you go up in the record length, it will change. Oh no, it looks like 10k is pretty quick as well. So, but let's go to 100k and see what happens. And as you see, as I scroll through that menu, it automatically selects that. So you don't have to select it, you just have to scroll through and it automatically changes things for you. I don't like that. Oh, I like to be able to scroll and select, please. But anyway, as you can see, we're at 100k points record length, and well, I'm not going to leave the camera running, so I'll let you know how long it takes. Oh, there we go, got it. Let's try the longer record lengths. One really annoying thing here, I'm not sure if I can get it, but this, as I scroll through, it seems to lock up occasionally. Look, I'm moving that, and it didn't move that menu option. It seems to lock up once it's on 20 meg. I don't know. Look, see, I'm spinning that, and it just sort of locks up, and that's what I generally find about this scope, and it's really quite annoying, is that things are very laggy and slow, and it's just, I don't know, it just really kind of bugs me. I expected more. I expected faster and better instant performance like you get on the Agilent ones for, you know, basically a $30,000 oscilloscope, modern one. On the 1 meg sample memory, I was actually able to capture that one in 18 seconds, but I think I'm lucky because it's taken a hell of a lot longer than that. It's now a minute past that, and it hasn't captured a second one yet. But yeah, I think I just got lucky, but it seems it's definitely slower as you go up in the memory depth. And we're up to 5 minutes here, and I've got it on 10 meg points, and it hasn't even captured the first one yet. That 5 minutes translates to only 3,000 waveform updates per second, and it still hasn't triggered it, so it's less than 3,000 for sure. Well, it could be either side. You've got to take an average of these things, but getting a bit tired of waiting. It's as slow as a wet week. 10 minutes. This is getting ridiculous. I think I'll go eat dinner. And I think I officially give up at 20 minutes. That equates to less than 830 odd waveform updates per second. Now, I know this waveform updates per second rate changes with the time base, but this is a direct comparison to the Agilent one, so I don't think it's unfair at all. So, yeah, this thing's got so much dead time, I think I'll go out the back and bury it. Check out this weird anomaly. I'm going to press the trigger level over here to actually press in the knob to set it to 50% and watch the display. Look at that. What? What is that? Unbelievable. And let's do a test to see if we get any aliasing. Let's turn, that's a 20 megahertz sine wave, by the way. Let's turn it down, and yep, we do. Check it out. Alias City. But of course you won't get that if you choose a longer memory depth, like 1 meg. We're still getting something there, and then 10 meg. Nah, she's all still sweet. There we go. I'll show you a little trick with determining the waveform update rate of a scope. Here's a little trick how you can actually measure it. Now, what I'm doing is I've actually got the output, the trigger output on the back of the Tektronix scope, okay, that auxiliary output, here it is, the aux output. I've got it set so that the output, it gives a pulse every time it triggers and starts a capture. So, bingo, by measuring the output frequency of that trigger event, we can determine the waveform update rate directly in hertz. So I've got it hooked into the frequency counter up here on the Agilent, and basically you want to look at the mean frequency here. So here it is, 4 kilohertz. So if we get out of here, that is the waveform update rate. You want to take the mean frequency out of that, but it's basically 4 kilohertz, 4,000 waveform updates per second at this current time base. So we can now determine, where are we? We're at 100 nano per division, and that's the waveform update rate isn't really changing a huge amount there between when I change the time base, but if I take it down, there we go, you'll see the waveform up here change. So let's see, I'm at 20 nanoseconds per division down here, measuring a 20 megahertz input signal, and we're basically getting, if I reset the stats up there, you probably can't see that, but I'll tell you it's 4 kilohertz or 3,000 samples, waveform updates per second, basically, and that's with only one channel going and only a 1K sample memory. And if we change that to 10K, you'll see it doesn't actually change that frequency at all. So 100K and 10K are the same, so is 100K sample memory. But if we drop it down to a meg, bingo, look at that, we've dropped down to 1K, 1,000 waveform updates per second. And if we go up even further to 10 meg, there we go, exactly the same time base, and we're looking at 20, basically 200 waveform updates per second, and we go down to 20 meg sample points, and whoa, we're not even in the ballpark here. 20 hertz. So there you go, 20 waveform updates per second at that particular 20 nanosecond per division time base with 20 meg sample memory. So that's a neat way that you can actually measure the waveform update rate of a scope. Now watch this. As you can see the pulses, the trigger pulses there, and they're basically that far apart, or 1.5 divisions or thereabouts. Now, I've only got one channel on at the moment. I've got 1,000 1K sample memory. Let's turn on a second channel, see if it makes a difference. No, it doesn't. So obviously the waveform updates per second stay the same with 1 and 2 channels on. Let's turn a third channel on, and hey, bingo, look at that. It has doubled. The waveform updates per second has halved to 1.5 K waveform updates per second. So there you go. If you switch on 4, it's exactly the same. So it looks like there's one chip inside handling 2 channels, but as soon as you turn on the second channel, bingo, you halve your waveform updates per second. So let's turn off number 4 there, and let's turn off number 2, and no, so there you go. Maybe there's not a chip sharing. It's just once you go more than 2 channels, so I can turn on channel 1 and channel 4, and it has the same update rate, but as soon as I turn on a third channel, bingo, it halves. Another thing I find rather annoying is the lag in the vertical look at the label there, which shows the ground point, that 1 there, and the waveform takes a long time to follow it. I don't know if that's deliberate or not, but you know, and sort of that's the fastest sort of update rate you can get. I've got a small amount of sample memory depth, and even on waveforms that do you know, nothing, you know, it's just, I expected better. And of course, one thing I forgot to mention with the RF, if it wasn't actually obvious, it's fully integrated into the triggering system. So if we go to the trigger menu over here, all your basic trigger types, but your source itself can actually come from the RF power level, and not only just edge types, but other types as well. So one thing you'll find lacking there, of course, is the external trigger. As I mentioned, with this scope doesn't have an external trigger. You have to sacrifice one of the analog channels if you want that. But it's incredibly powerful when you can trigger from your RF source. So as soon as your RF transmitter turns on, or it reaches a certain level or drops below a certain level, bang, you can trigger your scope. Brilliant. And of course, with your display, not only can you have math waveforms, you know, it does FFTs. You can do and math FFT if you really want to, but there it is there. But you know, when you got a real spectrum analyzer built in, but I guess that's handy for when you actually capture analog data and you want to look at it later. That's pretty good. And also we've got not only can you turn on a math waveform as well as the RF, so you can have, bingo, there's your RF waveform, you can have your math, your digital, and so it really is a mixed domain oscilloscope, you know, as the name says. And you can turn on 4 types of buses as well, digital buses, SPI or you know, I2C or something else. Brilliant. It's almost too much to display, as well as the digital, because you can turn on, you know, the 16 digital channels plus frequency. It's got everything but the kitchen sink. Now I'll show you how turning on the various functions actually slows this down. Now you can get an idea of the update rate there, and we're at 100k length there for the memory, so it's updating. You know, it's updating fairly quickly. And we've got all 4 channels on there as a reference. Now if I go turn the digital channels on, you can see it sort of start to stutter there just a little bit. And let's turn the math on. Do that FFT, and then it stops, freezes. So there he goes, and then you know, if you turn on a couple of buses like this, and you can see the stutter in the buses there. So as you start to turn on all these features, it really starts to slow the thing down. Well, as you'd expect, but you know, for this sort of, you know, $30,000 hardware, I sort of expected it to, you know, have a bit better performance than this. So really, as a basic everyday use scope, it just, I don't think it really cuts it for the price. I mean, you know, this is a $20,000 instrument. Granted, it's got the RF, but if we look at the MSO 4000 or the DPO 4000 series, which is exactly the same oscilloscope under the hood here, except it hasn't got the RF, well, I don't know, it just gets blown away by the Agilent X Series. They just don't have anything to match it. So, geez, give me as an everyday scope, give me the Agilent any day of the week. And no surprises whatsoever on the VGA display here. It just duplicates what's on the screen in XGA mode. Works brilliantly. Let's see what happens when we plug in a USB key here. Does it detect anything? No, doesn't do a thing. One really nice feature is that you can actually assign different functions to the save button down here, so you can set it up easily and then just hit bang, save. Well, it doesn't seem to recognize my USB stick here. I don't know what's going on. Well, I checked the stick on my computer. I've tried all 4 ports, including the 2 on the back, and it still says no drive mounted, and my computer can read that memory stick no problems. No idea what's going on. Let's try some different memory sticks. I can't get this stupid thing to work at all. Menu off. Save. Media is missing. Insert a look, hey, I can see my LED flashing on there. It's flashing away, but on my stick, but it just says it doesn't like the media. I don't know what's going on here. This sort of stuff you just expect to work. It's ridiculous. Okay, for some reason it's just decided to work with this memory stick here. It just, okay, right, file format, you can switch between PNG, TIFF and bitmap. Great, fantastic, save it. And you can save the screen, dump the screen waveform, and I'll have to go inside on the computer and check to make sure that works. But you know, you can save the waveforms or the screen image and other things, and you can just assign it to the save button. So that's pretty good. But I don't know, something buggy with this USB memory stick thing. I have no idea. Here's another example of just the general lagginess of the scope, and I don't understand this. In this case, I've set up a marker here on this transition event, and if I use the pan control over here and I pan around like that, you'll notice that the white triangular marker there actually leads, it leads the transition event. Why? Why does it do that? I don't understand. It should follow that transition event precisely. Is that done on purpose? Crazy. Okay, I think I might have figured out a possible reason here. If I actually move that marker across and I suddenly let go of the control, bang, it catches, the waveform catches up to the marker. So if you follow the marker is where you want to actually put something, and then the waveform eventually follows across. But if you don't have a marker, if you actually clear all the, how do you clear the markers? Anyway, if you clear all of them, then you can, then the pan control, it always kind of overshoots. If I'm moving my waveform across and I want to stop and I release my hand, it's a, you know, there's like a half-second delay before it actually physically stops there, and I don't like that. I find that, and same thing goes with the multi-purpose menu selection button. I find I'm always sort of overshooting things, and it's just really annoying. I don't think they've tweaked that as well as they can, but I don't know, personal opinion maybe, but I just don't like it. I find it rather annoying. Now here's one really annoying thing. The vertical gain control actually has a nice little indent in there. Now I expect every time I turn that indent for it to change scale, but I've noticed sometimes I change it and I turn it one indent and it does nothing. It doesn't actually respond. I probably won't be able to get it to duplicate that here, because Murphy's Law and the white coat. There we go. I got it. I turned that and it did not go down one scale. What's going on? It's crazy. It's like this thing is so slow that it can't respond to various you know, knob things and key presses. It's just crazy. And here's yet more freezing of the display. I've got a low amplitude signal here at 20 megahertz, and I'm on the 20 meg record length, okay? And it's updating, you know, it's fairly slowly, but it's updating because it's 20 meg points. Okay, fair enough, I'll give it that. Look, I turn on this bus. Look, it's practically stopped. It has stopped updating. Look, it'll occasionally go, and there'll be a little burst if I turn on another one. Oh, there's a little burst. What? And I'm triggering from that channel. I'm triggering from channel 1. So what's going on? And here's an example of the math updating versus the record length. Now I've turned it down to 1000. You can see the math updates pretty quick. We go to 10k, maybe a little bit 100k, a bit slower. 1 meg. Clunk, 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 clunk. It really is having a hard time churning through all that record. Go to 10 meg. Twiddle your thumbs. Hey, there we go. We had an update. Oh, beautiful. What was that? One update every 5 seconds or something like that? Go to 20 meg. Forget it. It's getting a bit tiring showing how slow this thing is, but look, I hit the default setup down the bottom here, so I can't be accused of having it set up wrong. I've got nothing else turned on. I've just got channel 1 just sitting there, just measuring some noise, okay, on 20 nanoseconds per division at 10k record length, and just look at the update speed. It's slow. I can practically count that fast. But if you compare that to the Agilent 3000 display at exactly the same time base, it's absolutely screaming along. No contest. And the good news is it does go down to 1 millivolt per division. It's not bad at all. I've got a 50 ohm terminated input here, and but that's set to 1 meg input, and it's about 1 division there, so about 1 millivolt of noise in that mode. And if we switch to 50 ohm terminated mode, it kind of almost halves, and that's on full bandwidth, by the way. And if we change the bandwidth here, we can lower the bandwidth to 20 megahertz. That's not bad at all. I like it. And if we take off the terminator there, no, it stays exactly the same. At pretty much the terminator makes no difference. I really like it. Now, it comes with the National Instruments LabVIEW Signal Express Tektronix Edition software. Now, I tried to install this, and then it wanted me to, I don't know, like call an operator or something, call an actual human, so that I could get some license code to install it. Well, screw that. So I didn't bother. And it also comes with the Tektronix Open Choice software, which is the Visa it's a Visa compatible driver with this thing, and it crashed when I installed it. So yeah, I didn't bother with that either. So sorry, you don't get to see the PC capabilities, but I'm sure it ultimately will work. Maybe. I think I'll call it quits there in terms of the review, because there's just so many things in these modern scopes. It's crazy. I can't possibly mention and test everything. If you want to know about the other details and the specs, the manuals and data sheets are out there. Go take a look. Tell us the price, son. That's what everyone wants to know. How much does this baby cost? I've already mentioned it during the review. The cheapest one you can get, I've got the Tektronix prices here, I'm not going to get it wrong, is $19,900 US. What's that, $2 Australian these days? Anyway, that's for 500 megahertz analog bandwidth, 4 channels. It's only available in a 4-channel version. 16 channels digital. You can't get it without the digital, and with the 3 gigahertz RF spectrum analyzer. It goes up to $22,900 US if you want the 6 gig RF, or if you want the 1 gig analog, you're talking with the 3 gig RF, $24,900 US, and it jumps to top of the line model is $28,400 US. So it's almost 30 grand there. Now, here's a kicker. The MSO series, identical scope to this, except it doesn't have the RF. If you're talking the base model unit, it's still $16,200 US. So you're only paying $3,700 for the RF spectrum analyzer. And if you can afford $16K, if your company's going to pay $16K for an oscilloscope, you can squeeze a little bit more out of them and get for $19,000. Get this, pay almost three and a half grand more. Get the spectrum analyzer. I highly recommend it. I don't know. I think this might even almost kill the MSO market, because I think you'd be crazy to buy the MSO version when you can get this for not a huge amount more. At least for the 3 gig version, it's an extra $6,700 if you want the 6 gig RF spectrum analyzer, but the 3 gig one's going to be very handy as well, so I highly recommend you get it. And of course, that doesn't include any of the options which I mentioned, and the cheapest option you can get is like $870 odd. The others are like $1,280 and more. One module's even $4,700. Give me a break. It's an absolute rip-off. Even if you just want to do basic stuff like RS-232 triggering, jeez. So this puppy is not cheap at all. It costs an absolute buttload of money, 20 or 30 grand, and then when you get the options to make it kind of useful, or more useful, man, the sky's the limit. If you have to ask the price, you can't afford it. But is it worth it? You bet. It's worth every freaking cent. It's unbelievable. The RF mixed domain capability, it works, and they've got it right. It's brilliant. So if you're into RF design at all, you probably wouldn't even read this review. You'd watch this review. You'd probably be racing out to buy one already. It's just brilliant. But you don't have to really be into RF to actually make use of the spectrum analyzer built-in. You know, things like EMI these days is a big problem. Let's say you wanted to check what happens when your huge grunty parallel output X Series output driver or something, you know, all the states change at once and gulps a huge amount of current from the power supply. Well, what does that do to your EMI? Well, you can find out with this baby. It's brilliant. You can sort out all your problems. I wish every scope had mixed domain capability. So I think this pretty much is the big revolution that Tektronix claim it to be, and I don't know how long it'll take before the others catch up and have mixed domain capability, but I'm very, very impressed. I want one. Will it actually earn a space here on the EEVblog rack behind me? No, unfortunately not. I've got to send it back. What a bummer. Anyway, as much as impressed as I am with the MDO capability, I'm very, very disappointed in the that they've done nothing. They've made no advance to their MSO series. They've just taken the MSO4000 series scope and bolted the RF on. Granted, it's a great addition, but they haven't made any advances. There was just so many things in this thing that annoy me as just a regular, everyday oscilloscope. And in terms of its performance and its speed and the quirkiness of the user interface, man, there's some great aspects to it too, but it just annoys me. Can't get over it. I wouldn't want this thing on my bench as a regular, everyday use scope. But it's like the big instrument you bring out, when you really have to solve your problems. But everyday use, it'd probably annoy the hell out of me. And that's the kicker, right? This thing starts at $20,000. And if you're talking about the let's just talk about the MSO 4000 series for a second. That starts at over $16,000. Now, that is, that's $4,000 more than the top of the line Agilent 3000 series, even though they're not supposed to be directly compared, because this is supposed to be not as equivalents. Performance just blows it out of the park, and you can get that performance on a sub $3,000 bottom of the range unit, and you pay your 16 grand for one of these, and it's just slow as a wet week. Very disappointed. The equivalent top of the line Agilent X Series is only $11K, and the options are cheaper. Man, between the MSO 4000, it's a no-brainer. Go for the Agilent. But if Tektronix can get this MDO thing right, then I'd love to see it when they actually put some R&D resources into a new generation of baseline scopes to improve the performance. Can't wait. Come on, Tektronix, where's your answer to the Agilent X Series? Bottom line is though, would I recommend this? Even with all its little quirks? Absolutely. It's worth every cent. Don't walk, run to buy one of these if you can afford it. Now, Tektronix were originally quite reluctant to let me do a teardown on this thing because they were afraid that I might break their precious $30,000 oscilloscope, but they finally relented, so we've got a teardown coming up. Check it out. But they didn't say I couldn't do a drop test, and we love doing drop tests here on the EEVblog, so why the hell not? Let's drop it. Oh. Yeah, don't try that at home.